Hello again. This is a second part video to the topic domain and range. In the first video, I identified what the domain and range is and how it correlates to a relation and how to do the vertical line test. In this particular video, I'm going to focus on some functions, and we're going to practice finding the domain and range for those. So I'm going to talk about a few common things to look for, so I'll try to keep the video as concise as possible. So let's say you had, when you have polynomial functions, okay, right, okay, so an example, if you have like y equals x squared plus 5x minus 5, okay, and you were to you want to find the domain and range. If you were to graph that, that's going to look like a parabola, a right side up parabola, and it's basically going to tell you that when you want to find the domain, you want to find all the x values, okay? Well, you want to ask yourself, when you do the domain and range, are there any restrictions? In other words, can I plug in anything I want for x and get a corresponding y value? Well, you can. So the easy way to determine the domain and range for a lot of functions is you want to look for restrictions, interruptions, square roots, and fractions. Fractions and square roots will have restrictions. But if you have a function that is not a fraction or doesn't have a square root operation in it, then it's going to be unlimited choices that you can put in for the value of x, okay? So when you graph this, when you graph this, it's going to look like a parabola, okay? So basically, the domain is going to be negative infinity to positive infinity, and we always use parentheses around infinities. That means that you can plug in, okay, you see this here? You can plug in any value with no restrictions. Okay, there's nothing that's going to stop you. You can put in a decimal, you can put in a fraction for x, you can substitute a whole number, or you can substitute a negative or a positive whole number. The sky is the limit. All right, no matter what you put in for x and compute it, you're going to get a corresponding y value, and when you get all those points, okay, you connect them and you're going to get a parabola. So in this particular situation, the domain is not restricted. It's literally unlimited. Same thing when you have a linear function. Let's say you had Let's say you had y equals 2x plus 1, okay? And if you graph that, you're going to get a line. Okay, remember the 1 is the y-intercept, so that would be your first point. Okay, and then the slope is going to be 2, so that means you go up 2 over 1. And I had videos on how to do this, on how to graph lines, how to graph linear functions in the slope-intercept form. Okay, so when you graph it, you're going to get a straight line that's going to look like that. Okay, that's just going to go on forever. So the domain, the x values are not restricted. You can put in whatever you want. And when that occurs, again, the domain is going to be, okay, negative infinity, comma, positive infinity. There's no restrictions for these kind of functions, as long as there's no fractions or square root signs, okay? So when you see a function like that, it's automatically domain is infinity. And also the range is the same thing. The range is not restricted because whatever x value you plug in, you're going to get a corresponding y value. So the range is going to be equally the same. There's no restrictions. If there's no restrictions for the x, in this case, there's going to be no restrictions for the y, because whatever you get for an x, you're going to get a matching y value. You put in another x value, you're going to get another y value. And you can do that till infinity, and you'll always have that input versus output, okay? And same thing goes for this. So I'm going to put r for range. It's going to be negative infinity to positive infinity. Okay, so there is no restrictions for this. For this particular video, I'm going to draw your attention to the domain because that's what we want to pay attention to more than anything. So if you have a rational function, right, so when we talk about rational functions, now we have to be careful because rational means that it can be expressed as a fraction, and fractions do have limitations. When you have a rational expression, you have a numerator and a denominator, and it's the denominator that is the problem, okay? So let me give you an example, all right? So let's say you had f of x equals 3x minus 4 divided by x plus 6. That is a rational expression, which means you have a fraction with a fraction containing polynomials, okay? So when you have a fraction that contains polynomials, then it's called a rational expression, okay? Rational means it can be expressed as a fraction. That's clearly a fraction. Maybe not be a nice fraction, but it's a fraction, okay? And what we want to do is we want to focus on the denominator, not so the numerator. The numerator can kind of be whatever it wants, but the denominator is, we have restriction. And the reason why is because we can divide anything, okay? We can take something and divide it by any quantity with the exception of 0, okay? So the key thing to keep in mind is that we cannot divide any quantity by 0. Because if you do that on your calculator, you'll get an error message or a syntax error message, which means you can't do it. It's not permissible, okay? It's considered undefined in mathematics, okay? So that's considered undefined. All right, and there is a value that we can plug into the denominator that will make this function undefined, and there's only one way to find out, okay? So when you do this, okay, let's go ahead and write whatever the denominator is and set it equal to 0 and solve for x. Why do we want to do that? Because that's going to give me the restriction that the denominator cannot be for x. All right, so if I solve this, if I take x plus 6, which is the denominator, set it equal to 0, that forms a nice little simple equation. Go ahead and solve it by getting the x by itself. So we're going to subtract 6, and then you're just left with x equals minus 6. So that means that the domain can be anything with the exception of negative 6. Okay, so if I check it and I plug in negative 6, then that's going to equal 0. And I can't take 3x minus 4 and I can't divide that by 0. That's going to give me an undefined situation. So the value that we need to stay away from is x minus 6. That is going to make the denominator undefined. So when we write the domain, we can say the domain is all real numbers except -6. Okay? We're not going to be able to use -6. All right? So the domain can be is all real numbers except 6. Okay? You can also write it in set builder notation if you want. Okay, and if you do it that way, then you can say, okay, for all values x such that x cannot equal -6. That's another way. You got set builder notation. All right? We could practice that when we do another example. Okay, so we want to make sure that, you know, we understand the basics. Okay, so that is what's going to happen with it. So let's look at another example, okay, of a rational function. And when I do this, I'm going to show you the restriction, how to find the restriction that we just did. I'm going to show you how to write it in words, how to write it in set builder notation, and then how to write it in interval notation. So we'll do all three, okay? And that way you can make a nice comparison of how to do it. All right, it's not that hard. Again, when we do the domain for a rational function, we want to look at the denominator. Don't worry about what the numerator is. And then you just take that and then you say, okay, we're going to set it equal to 0 and solve for x, which is super simple. Subtract 2 on both sides. And then you're just left with x equals -2. Okay, so here's 3 ways you can express the domain. And the question is going to ask you, what is the domain of the function? Okay? So you can say the domain is all real numbers except -2. Okay? If you want the set builder notation, then you're going to say, for all values of x such that x cannot equal -2. So that means when we have a set of numbers, that's indicated by the braces, right? Within this set of numbers that go on for infinity, we want every one of them except x not equaling -2. Okay? And if you want the interval notation, then remember if we're including every single number from -infinity to +infinity, with the exception of just one number, then we just write this. -infinity, comma, -2, parentheses. That means we're including every single negative number all the way up to -2, but not including it. That's why I'm putting the parentheses around the -2. And then there's a union because there's a gap. We're not including -2, so that creates the hole, okay? And then we can pick up everything above -2 all the way to +infinity, okay? All right, and that's what it would be, okay? So that is one way you can do it, okay? And that's it, okay? That's a good example of that. So identify the denominator, set the denominator equal to 0, solve for it. That'll tell you what the exception is, what the domain cannot be. So you're going to say the domain is all real numbers except that value, and then follow 3 options you have: set builder notation or interval notation, okay? Okay, so what I did here was I solved a rational function where we take 3x plus 4 and we set it equal to 0, and then we solve that for x and we get negative 4/3. And solving that simple equation gives you the domain that cannot be used. So then we say the domain is all real numbers except negative 4/3, because on the number line we're excluding it, all right? Except means we're excluding it. So once we take 3x plus 4 equals 0 and we isolate the x, we get x is negative 4/3. That's the exclusion. So that's why we say the domain can be any real number on that number line with the exception of negative 4/3. And then, of course, if you write it in set builder notation in the braces, then it would be all values x such that x cannot equal negative 4/3. You got to put not equal because you're saying it's except, all real numbers except that one. All right. When you do the interval notation, then it's negative infinity to negative 4/3, but we put a parenthesis around the negative 4/3 because we're not including it. And that's going to leave a hole in the gap on the number line. That's going to leave a hole right at negative 4/3. So you need to put that U or that union symbol indicating that there's a gap there. And then we pick up from negative 4/3 again, but we're not including it. So we put the parentheses all the way to positive infinity. So you got three options of writing your domain here. Any three would be acceptable. Now I want to talk about the other type of function, which is radical functions. Radical. Okay. So radical functions are going to have the square root sign. Okay. So an example of this would be square root of x plus 7. Now, just like fractions, radicals have exceptions too. Just like we can't divide by 0 in a rational function, there's an exception here as well, and that is you cannot take the square root of a negative number. Okay, so this would be considered a complex solution. Okay. Complex numbers are a different category of numbers. They're not real numbers. So anytime you take the square root of a negative number, for example, a negative 1, okay, is going to be considered an I or imaginary, okay? Which is the same thing. Whoa, I'm so sorry. This is so difficult to write today on this thing. Sorry about that. That's an imaginary number, okay? And that's a whole different set of numbers. So what am I trying to say is that if you attempt to take the square root of a negative number on your calculator, it's going to give you an error message because it's a complex number. Those have to be treated a little bit differently and worked out differently than real numbers, okay? Which is a whole nother lesson. But if you wanted to find the domain of the square root of x plus 7, it's going to look like this. So let me just show you what the graph looks like. Okay. And it's going to look like this. So this will be negative 7. This will be 2. It's going to look something like this. Okay, and you notice the graph doesn't go below 0 on the x-axis. All right. So here's what we want to do. We want to take the x plus 7, that's under the radical, right? And we want to set it greater than and equal to 0, because in order to take the square root of something, it has to be, the x value has to be 0 and above, okay? If it's below 0, you're going to get an error message. So we're going to set up an inequality. Whatever's under the radical, you're going to say greater than and equal to 0. Then you're going to solve for x so that these will cancel. Then you're just going to be left with, okay, x is greater than and equal to -7. So that means my domain has to be all values greater than and equal to -7 in order for me to take the square root under that radical. Okay, so again, you can write it in 3 ways. Okay, so you can say the domain is all real numbers that are greater than and equal to -7, okay? Or you can write it in set builder notation. You can say all values x such that x is greater than and equal to -7, okay? And for interval notation, greater than and equal to is going to be a bracket, and it's going to be facing towards the right. And we're going to include -7 all the way to positive infinity. That would be the interval notation for that. Okay? So you can express it in many different ways, because think about it, if you graph x is greater than and equal to -7, you use a bracket, right? Going to the right, and you shade everything to the right in the positive infinity direction. And that's why you want to use the interval notation bracket to include -7 facing towards the right, comma, all the way to positive infinity. So radical functions do have limitations as well. Okay? So it's just something to keep in mind. So another example of a radical function is, let's say you had f of x equals the square root of 6 minus x. Okay, so we're going to take 6 minus x and we're going to set it greater than and equal to 0, and we're going to start solving for x. Okay, so I would probably just go ahead and subtract the 6. So then you have minus x greater than and equal to -6. But we have to divide by that -1, that invisible -1, so that the negatives cancel, and then you're just left with x. -6 divided by a -1 is a +6. But anytime we divide by a negative, we have to reverse the inequality sign. So therefore, my domain, okay, my domain is all real numbers that are less than and equal to 6. You want to write that in set builder notation, and it's all values x such that x is less than and equal to 6. If you want the infinity, the interval notation, again, if you graph this, put 6 on a number line, less than and equal to is a bracket facing to my left, and that would be a negative infinity. So my interval notation is clearly going to be negative infinity, comma, 6, bracket. We'll put the close parentheses around infinities. So your domain is restricted with radical functions and rational functions. But if it's just a polynomial function or a linear function, then it's unlimited. There's no restrictions at all. And those are the 3 categories that you have to worry about. I hope that this video helped clarify to identify the 3 possible scenarios for domain. I hope you found this very helpful. Thank you so much for watching, and I'll see you in the next video.